Hey Pre-Calc, today is 8.4 vectors. Vectors, yes, like physics. Hopefully if you are upperclassmen, you've seen this in physics. It'll be a review hopefully, or if not, we'll learn it now. And physics vectors comes up a lot on the SAT. So keep that in mind as you are taking notes and trying to memorize the properties of vectors that we go through today. Now, the vectors are pretty visual, so I'm going to show you my notes as I'm going through the notes so we can do those together. Go ahead and have your book open to page 607, please, and get your notes out and date them for 8.4 vectors. Okay, so I've got my notes here, 8.4. Vectors, page 607 is open, and we have our two vocab words here that we have scalar and vector. And don't be worried too much by these. Scalar is just all those things that we've been looking at before, like length. And all of a sudden we're going to give it a direction, and so now we call it a vector. Length, scalar examples, length, area, mass, temperature, energy. They have a quantity, like a size, like something we can measure, but they don't have a direction. And then vectors, now we have they also have a magnitude. They still have that size, that quantity, that length, that distance, something, some number, but they also have a direction now. And those directions can kind of look different, but in some way they have a direction. So velocity is a speed plus a direction. We could have displacement, we could have acceleration and force. Acceleration, think like gravity, negative 9.81 meters per second squared. The negative of that 9.8 tells you the direction, that it's that downward direction towards the center of the earth. So that is a direction which makes gravity a vector. Now, it's possible you might be able to see these kind of talked as if they were a scalar and not have a direction attached with them. So just keep that in mind. So these are vectors when they do have a direction attached to them. Okay, so just your definitions there. Let's take a look at what a vector looks like. Here I've got this is a vector here in pink. A is the initial point, B is the terminal point. We know that because of the arrow. The arrow is pointing towards the terminal point. That's where it's starting and ending with the arrow, okay? And we also use a bolded shape or a bolded letter to denote a vector. So this is a bolded lowercase u to represent that vector A to B, that arrow above it. The magnitude, think of it like the size or the length. Right up there we had magnitudes. These are all like lengths and sizes. So the magnitude is just the absolute value of from A to B. So it's the length there. We use bold-faced letters to denote vectors. Okay. Next, we have a blue box on page 610, and this is going to be vital. There's actually several blue boxes, like a ton in this section. All will be helpful. I don't know if we'll have time to get through all, but if you're studying for the SAT, I would go find all the blue boxes in section 8.4 and make sure that you are feeling good about them, understand them, maybe copy them into your notes, do some extension, extra problems with it. So we have magnitude or length of a vector, V, bolded V, and we have these kind of weird looking parentheses, pointy things, A to B is showing the vector there from A to B is, so the magnitude or length, the length is going to be the absolute value of square root of A squared plus B squared. And I'll show you what that looks like and why we use that in just a second. So if U equals A1, B1, and V equals A2, B2, we can add them, and you're really just adding the two A's, and then you add the two B's, and that's your new vector answer. Subtraction, same thing, A minus B, and then a B minus B. Keep it in order, of course, order matters. And then C, what if we were to multiply it? What if I wanted to double the vector, 2V? I'd multiply 2 times the A and 2 times the B. And that works for any real number. Your C, your multiplier, could be any real number. It could be a half. You could take a half. You could take a fraction, a whole number, an integer. You could take a decimal, a negative, just as long as it's a real number. Okay? So let's take a look at a couple things. So here's one vector. So this vector is starting here, and it's ending there. I haven't named it yet. It has a length of 2 diagonal boxes. If we're counting, if this is, real graph paper by ones, that's 1, that's 2, that's 1, that's 2, and if I were to draw another one right there, this is going to be an equal vector. I have the same exact length. I went 2 diagonal boxes there. Same exact length, and I'm going the same direction. I'm going 2 to the right and 2 up, 2 to the right, 2 up. Or you could say I'm going northwest, or you could say I'm going 45 degrees. So these are going to be equal. What if I move one down here? Also going to be equal. Over here, also going to be equal. Right on top of it, also going to be equal. Over here, also going to be equal. Okay, so these are all going to be equal. And why are they equal? It's because they have the same magnitude and direction. They have the same magnitude and the same direction. As soon as I go and draw one going this direction, it has the same magnitude. I'm still going a length of 2 diagonals of the boxes. It has the same magnitude, but it doesn't have the same direction. Now it's going northwest instead of northeast. And this is not going to be an equal vector to the others. What if I keep it in the same direction, but I go 3 diagonal boxes? So it's still going to the northeast at the same 45-degree angle, but instead of going 2 diagonal boxes, I went 3. So it's the same magnitude, but different direction. So these are not going to be equal vectors. Okay? Next, let's look at, I have 2 vectors. Here's vector u. U starts here and ends there. V starts here and has a terminal point there. And I am asked to add u plus v, and those are bolded, of course. I'm asked to add u plus v, and simply we got to connect them like so. And easy enough, that is our final answer. That green is our answer vector of a u plus v. And we may be asked to determine what that is. So you might have a coordinate here. You might be giving me what that is. Let's see if we're starting at, let's say that is 0, 0. Over 1, 2, 3, 4, 5, up 1, 2, 3, 4, 5. So that point may be 5, 5 if we had started at 0, 0 here. And you may be asked to give the direction. So you will be asked to give a direction. It's a vector. So here, look at, we went 5 boxes over, 5 boxes up. So we know that 5 and 5, that's a isosceles triangle, right? Those are the same 2 sides. This is a 45-degree angle. Here you could have done, whoops, not percent, angle. 45-degree angle, and we'll call that theta there. So our direction there is 45 degrees. Now the length, so we need the magnitude, which will be the length of u and v. If you look at this, this is a, as we just said, it's equilateral, a right triangle. So think back to your geometry. You've got a, if these were named A, B, and C, and if this were a right angle, you can use the Pythagorean theorem, a squared plus b squared equals c squared, which, if you take the square root of c, so here's a squared plus b squared is supposed to equal c squared, but I took the square root of both sides, so it's c equals square root a, the square root of a squared plus b squared, which is up here. We have this in our blue box. The magnitude or length is going to be equal to the absolute value of a squared plus b squared. And that's coming from the Pythagorean theorem. So even though I didn't have a right triangle in my vectors, that was the pink here, I drew it in because we're on graph paper. We counted 5 to the right and 5 up to get to that point there. So let's do it. We have a 5 squared plus a 5 squared, and the square root of 25 plus 25 is 50. So we have square root, so c equals square root of 50. We would see if there's any GCFs in there. There's 2 pairs of 5s and a pair of 2s. So that reduces to a 5 radical 2. So our length of UV, we have our magnitude is 5 radical 2, and our theta is 45 degrees, and that is our U plus V. Okay. All right, let's take a look at another one like that. What if we're adding this one, adding this U plus V? I've got U here, initial point, terminal point. Here's V, initial point, and terminal point. So we're asked to add these two, and I am just going to go ahead and draw in what the addition of them looks like. Okay, and so this is a start, arrow here, arrow here. So this is the arrow of our vector U plus V. And U plus V, I need to know 1, the direction, and 2, the magnitude. So magnitude, let's recall that we have our absolute value of the vector, the magnitude, is going to be equal to the square root of a squared plus b squared. Let's see if I'm starting here. So this is our start, and this is our finish. Starting here, how do I get to that point? We go over, so x is first. 1, 2, 3, 4, 5, 6. So my change in x, my delta x, is a -6 units, or 6 to the left. 6 to the left, or -6. So that's my delta x, and then how do I get to this point? I went down 1, 2, 3, 4, 5. So delta y equals 5. We went down, so that is a -5. -5 there. All right, a squared plus b squared. We could have gone to, if you wanted, since it's just the Pythagorean, we're going 1, 2, 3, 4, 5 down that way, and then you would have done 6 left that way. You could have gone that way too. That's fine. Let's plug in. We're going to have a -5 squared or -6 squared, and then the other one, a -6 squared. All right, you're squaring even the negatives, so those make those positive. We have a 25 plus 36 under the radical, which is a square root 61. And so our magnitude, our answer there, is a 61, square root 61. And we also need the direction. And this is not 45 degrees anymore. And let's see. Does it want us to give? Let's just say southwest for now. Let's say southwest for now. We'll come back to this and get the angle there for theta. Okay. Let's talk about finding. So we have 2 vectors here, a u and a v. Let's find, your homework's going to ask you this, and often the SAT might do this too. They like to give you a visual first. So let's find some different things. So we've got a 2u. So 2u, and this goes back to our table of c. When we multiply a c on, you multiply that c onto the a and the b value. So let's find out what is the value there at u and at v. So v is at 3 up at 2. Let's name those. U is at -1, 3. Okay, so if I'm doing 2u, that's going to be 2 times where u's terminal point is. And so think of it like a distribution problem. And we have 2 times -1 and a 2 times 3. So your answer there is a -2, 6. Okay. The properties for this are on page 611. They've got a few different tables here of the properties of vectors and the algebraic operations in vectors, magnitude of vector. We should have that one in our notes already. So I'm doing right now the properties of vectors on 611. All of these are good to know and have. Okay, so -3u, negative, not as scary as you think. You're just distributing -3 onto the -1 and the 3. So negative, negative, we have a positive 3 and a negative 9 there. 2v, looking at v is a 3, 2, so we're multiplying that by 2. We're doubling it, right? What would this look like? This is like taking v out another, let's see, it was over 3 up 2. Be taking v out another one. This would be 2v, would end you up at that point right there. Okay, same with the 2u. 2u, we'd be doubling it out in that direction. So 6, 4. We've got a negative 4v. Our vector for v is 3, 2. Negative 4 times 3, we have a negative 12, negative 8. Okay, now u plus v. Well, our u is a negative 1, 3, and our v is 3, 2. And the properties we discussed, it was a1 plus a2, comma, b1 plus b2. So we're just adding the a's, adding the b's. Negative 1 plus 3 is a 2. 3 plus a 2 is a 5. Okay? Now subtracting here, order matters. You got to be careful with the negative. We've got a negative 1, 3 minus 3, 2. You could think of it as distributing the negatives, or think of it as a1 minus a2. Negative 1 minus 3 is a negative 4. b1 minus b2. 3 minus 2 is a 1. Okay, and then we have, and you will have this on the homework, a 3u minus 2v. So it's really a two-step problem. We have to multiply 3 onto the u and 2 onto the v, and then we can subtract them. Okay, following order of operations. So 3u, we've already done negative 3u, so let's flip the signs on that. So it's a negative 3, positive 9 will be a 3u. We say negative 3, positive 9. And we're going to minus 2v. We already did a 2v. It was a 6 and a 4. So let's subtract 6 and 4. And either think of it as distributing that negative or a1 minus b1 and b1 minus b2. So we have a negative 3 minus 6, negative 9. 9 minus 4 is a 5. All right. Next, we have page 609, component form of a vector. And some of your questions will ask you to put your answer into component form of that vector. So let's add this blue box into our notes for our notes today. If a vector v is represented in the plane with initial point p, x1, y1, and terminal point q, x2, y2, then the vector v, bolded lowercase v, equals x2 minus x1, comma, y2 minus y1. Okay, so I've added that into my notes here. Component form of a vector. And you'll see your homework questions will ask you express the following in component form. So it'll give you a drawn vector that you have to look at and find the component form for. So our first one, we've got from P to Q, and it's always going to be P is first. P is always going to be the initial, and Q is always going to be the terminal. But the arrow is going to tell you anyway. You'll know what the initial and terminal is from where the arrow is. So express in component form. So this is my 1 and this is my 2. Looking at your x, y, x and y is the 1s and 2s. So P, let's name P is going to be at 3, negative 1. So 3, negative 1, and this is my initial side. So let's name those x1, y1. And my Q, my terminal, this is at negative 1, positive 3. Negative 1, positive 3. And that is my terminal Q, so let's name those x2, y2. x2, y2. I'm going to copy down the formula for ourselves. x2 minus x1, y2 minus y1. So x2 is a negative 1. Oops. x2 is negative 1, and I'm going to subtract x1. x1 is a 3. And then y2 is a 3. minus y1, which is a negative 1. Careful, we're subtracting a negative 1, so subtracting a negative 1, that'll turn into a 3 plus 1. So our answer here, we have a negative 1 minus 3 for a negative 4, and a 3 plus 1 for a positive 4. And that'll be our vector answer expressed in component form. We've moved, and you can test it, we've moved 4 to the left, and we've moved 4 up. Okay, let's try another. We've got from P to Q, and it's the same instructions to express in component form. So let's name our P and Q. P is our initial, always our initial. We're over at 1, up at 2. That is our x1, y1. And our Q, over at negative 4, up at positive 1. That is our x2, y2. So x2 minus x1, that's a negative 4 minus 1. y2 minus y1, that's a 1 minus 2. Okay, negative 4 minus 1 is a negative 5, 1 minus 2 is a negative 1, and that is our answer in component form. And we can check it. We start here, we go negative 1, 2, 3, 4, 5, and a negative 1. There we go.